My name is Tianyang Zhang. I'm a PhD student in the Media and Network Lab in Tsinghua University. It's my honor to present our work, Come and Go Patterns of Group Evolution, a dynamic model. This work is cooperated with Peng Cui, Christos Flossis, Yunfei Lu, Hao Ye, Wen Wuzhu, and Tianyang. We know forming social group is an inherent human nature, and there are various kinds of groups all over the world. In our life, we have circle of friends, and in our society, we established a lot of companies and associations. And on the internet, we also have different kinds of groups in different social networks, such as Facebook or WeChat. Group is everywhere, and it is also a very important topic in both research and industry. It is one of the central building blocks of the modeling and understanding various social phenomena, such as information spreading, social tie formation, or social cooperation and competition. It also helps a lot in the practical use in various application scenarios, such as it can help us do advertising and marketing, topic detection or clustering, and anomaly detection, and so on. Social group also has been studied for many years as a fundamental problem in social science and network science. And they have studied the structure of groups and how to detect the communities in the network. They also studied the group formation and how the group grows through the underlying network. However, one limitation of past works is that they mainly focus on the spatial dimension of the groups. It means they use the structure information and study the structure properties of the groups. But another dimension, temporal dimension of social group, is also fundamental and important. We know that most of the social groups is evolving over the time, and no matter it is the circle of friends or companies or the online groups, it always changes and grows over time. We often want to know how fast will a social group grow. Will it grow bigger or gradually decline? What is the size of a group after 1 month or longer? These questions are related to the dynamics of social group. However, compared with the studies in the spatial dimension of social group, our knowledge about the temporal patterns of group evolution is quite limited. How to model the temporal process of group evolution, and it's still an open problem. So in this work, we focus on the group evolution process. We want to know how does group size change over time. So first, we want to discover the patterns of the different groups, and then we want to know what are the mechanisms behind the different patterns. And finally, we want to model different kinds of evolution process with a unified dynamic model. So first, we use a large real data set, WeChat group data set, to help us to discover the patterns of group evolution. WeChat is the largest social network in China. It has 700 million users. Yeah, and there are billions of groups in it because group is an important feature of WeChat. Every day, there are 2 million new groups established in WeChat. So we sampled 100,000 social groups from the WeChat dataset that with more than 40 members, large groups. We have the duration of 42 days since they are established. We have the records of the join and the quit log, and all the records contain the temporal information. So from the dataset, we can get the evolution process in the first 40 days of the groups. So we can observe a lot of complex patterns in this dataset. For example, some group may continuously increase in the first 40 days, and some may rise and stay. In some group, people just come and go, and it will decline over time. And we also witness the burst increase in some groups. We find there are so many different patterns in the group evolution process. And how can we find the mechanisms? So first, we find it's important. One important thing is that the group evolution process can be divided to two sub-processes. One is join process, and one is quit process. We call it come and go. So we want to know the mechanisms both in the join process and the quit process. So first, let's look at the join process. These are two examples, and the blue line is a blue dot is the real join process. Yeah, we can find that the join process is similar to an S-shaped curve. Yeah, on the beginning, it grows slow, and then speed up, and then slow to an upper limit. In fact, most group reach the upper limit in the first 30 days, the first month. And we also find that burst increase is very, very common in the social groups. About more than half of the groups contain burst growth. These observations indicate that there are two different mechanisms in the join process. The S-shaped increase and upper limited is similar to the epidemic spreading or information diffusion. That means in this mechanism, members in the group can invite their friends into the group, and the potential audience of the group is limited. So the growth speed is potential to the current size and the remaining potential audience. We call it diffusion mechanism because it is growth word of mouth. Another is the burst growth. Burst growth is caused by the external shock. For example, we have a conference here. Many people who doesn't know each other can join a group, form a group in a short days. So the new members are in weak relations with the current members maybe, and they are attracted by promotion or certain campaign or conference or some other external shock. We call it the non-diffusion mechanism, and it's the burst growth. So we can have the dynamic equation of join process. We have both diffusion growth and the burst growth. In the diffusion growth, we have two parameters. One beta, the infection rate beta presents the attractiveness of the group. And the population N is all the potential members of the group. We also need to know the group size to form the formulation. And also in burst growth, we have the time of external shock and its strength. And then let's look at the quit process. I think quit process is a little more complex. From the observation, we can find two different situations in quit process. The red dot is the quit process over time. In the first group, we find that it gradually gets stable, and the people who quit the group is slower and slower. And in the second group, we find that it continues decline over time. What are the difference between these two situations in the mechanisms? I think we can use the survival rate. That means how many percentage of people left longer than the time. Yeah, this is the survival rate. Let's see the survival rate of these two groups. We can find that in the first group, which gets stable, the quit rate is high at the beginning, but it gradually decays over holding time. But in the second group, it's almost a constant quit rate. From the data, we observe that most groups, the quit rate is decay over the holding time, and about 15% of the groups has a constant quit rate. These two situations indicate that they also have two different mechanisms in the quit process. The constant quit rate is similar to the recovery in the epidemic spreading. For example, the SIR model, it assumes that the constant rate to recover at any time. And we know that a constant quit rate leads to the exponential holding time distribution. This means no matter how long you have been in the group, the rate of your quit is the same. But in most groups, we find the quit rate is decaying. That means the longer you have been in the group, the less likely you are to quit the group because you become dependent or become loyalty to the group. So we find that quit rate decays in most groups, but the decay speed differs in different groups. So we also want to know how it decays over time. So we can use the holding time distribution to help us find how it decays. We know that if the quit rate is constant, it will generate an exponential distributed holding time. But in fact, the overall holding time distribution of all the groups is power law decayed rather than exponential decayed. That indicates that in this model, we need to generate both power law distributed and exponential distributed holding time. So we find that the quit rate of the group it decays over time, and we have the PDF of the holding time from this equation. We know we can find that if the exponent of the decay rate, alpha, if it equals to 0, it is an exact exponential distribution. And if it is larger than 1, it becomes a power law distribution. And if the exponent alpha is between 0 and 1, we can prove that the distribution is exponential-like with exponential tail, but it also has some power law in the middle time scale. So we can see the gamma determines the short time satisfaction degree. It mainly influences the short time quit rate. And alpha is the long-term dependence, determines in the long-term effect. So with the join process and the quit process, we can have our come and go model of the whole group evolution process. The group size is divided to the two sub-processes. I is the group size, and J is the join process, Q is quit process. In our model, we have the different mechanisms in both join process and the quit process. So to learn the model from real data, we need to first discrete the temporal process. Our model can be work in continuous time, but if we want to learn the parameter, I think it's a little too complex to use the continuous time model. So we can change the dynamic equation to the discrete time and convert the temporal data to a temporal sequence. And then we can use the LM method to minimize the error to train the 6 parameters of our model. And first, we can just ignore the burst growth. So we first train the 4 parameters and get our come and go based model. And then we can detect when there is a burst and learn the strength parameters later. So our model can fit the this is the showcase of our model. This is the 4 different patterns we showed before. And the red line is the result of our model, and another line is the result of SIR and SI model. We can find that we can fit all different patterns very well, and both in the join process, the blue, and the quit process, the red one. We can fit all this process very well. And we use RMSE to measure the fitting accuracy. We can find that the come and go base is that we don't consider the burst, and the come and go is that we consider all mechanisms. We can find that compared with SI and the SIR model, our model performs better than them. We decrease the RMSE by more than 50%. Another usage of our model is we can predict the size. Because we are a dynamic model, we only need the early stage data, and we can learn our model. And then we can predict the whole process at any time. So we use the first 15 days as the training data, and then we predict how the group growth evolves in the next 30 days. Here we use MAE to see the prediction power. We can see that our prediction result is much better than the result of SI and SIR model. Also, we can predict the group growth trends because in some situations we don't care the detailed group size, but we care if the group will grow or decline. Similar to the size prediction problem, we also use the early stage data to train our model, and we use the parameters to train a logistic regression model to classify the group into the growth group and the decline group. In the prediction problem, we achieve about 80% of the precision in both short-term prediction and the long-term prediction. So I think in this work, we find a new problem that is the dynamics of group evolution that is not studied before. And then we accomplished the three goals. First is we discovered the temporal patterns of the social group evolution. And we reviewed different mechanisms in both the join and the quit process of the group evolution. Finally, we proposed a novel unified model. The unified model can fit different patterns accurately, and it has strong predicting power. So this is what we do in this work. Thanks. Any
questions at the two ends? Yeah, go ahead.
Hi. So it seems to me that the quit process and join process should also depend on the structure of the group. Not just, so how do you incorporate that beyond just the size?
Yeah, good question. We know that structure have, the mechanism behind it is influenced by the structure. We all know that. So in the join process, we can see that the diffusion growth is similar to an SI model. That means the beta is the increase rate, and the n is the population. You can see there is a simple assumption about the structure. That means this is the people in the group I, and this are the people out of the group but has links with the group with the members in the group. And we have the beta is the increase rate. That means how can the possibility you invite your friends into the group. So the assumption of the mechanism is based on the structure. And in the quit process, we also have the alpha rate. Alpha is the decay rate. We find that in the if the structure is density, the alpha is always large because it tends to be large because in a closed group, people are more loyalty to the group, and over the time they are less likely to quit. But if the structure is not dense, yeah, people are more likely to quit. So we didn't have the structure data, but in the mechanism we consider the structure. Yeah, thank you.
Thank you.
I have one more question. Can you go back to the slides with the equation n, j, and I? So doesn't n also change over time as well? The number of candidates for the join process.
Yeah.
The capital N.
It doesn't change over time.
It doesn't change. Why? Because you assume n is the people that are not in the group, but with a connection with the member in the group. If you grow your member base, then you should grow n as well, right?
A good question. We think that a group is of certain topic, and the people who are interested in this topic it doesn't change very fast. For example, you have many friends. The number of your friends is always increased over time. But who are interested in the group, maybe when you establish the group, maybe the population will not change.
So
we
n,
assume it is a constant.
So n can be someone doesn't have a connection with the member in the group at the beginning stage.
if you don't have the connection with anyone in, we use the non-diffusion mechanism this term. And we can see maybe there is an external shock. For example, we come to attend a conference. Maybe we not know each other before, but many people may join a group. So it's a shock.
Great, thank you.
Thank you.
Okay, thank you so much. Let's thank the speaker.
Yeah, thank you very much.